Hello, we will continue our discussion on neural networks. We will now look at another interesting special neural network called the recurrence neural network. Recap our discussion of linear conditional random fields, which we discussed as an extension of the logistic regression model. The way we extended was to generalize a feature as a function not only of the input but also of the output. So we could have phi y1, y2 and phi y2, y3 and so on. The intent here is that any inference that was made based on a observation at a previous time step or at a previous position such as x1 and its inference y1 has implications on the inference that happens at the next time step based on the new signal x2, and the inference y2 at the second time step has implications on the inference at the next time step and so on. Now what we have done so far is not only looked at the generalization in the output space, we have also created a cascade of logistic regression models on the input front to create a neural network, a highly nonlinear classification model. So the question is, what if in a model such as a conditional random field you were to replace the input, that is the LHS here, the left hand side, with a cascade of say logistic regression or any other activation models. So this basically brings us to recurrent neural networks. Our goal is to be able to make prediction on sequence data, where the sequence could come from either temporal sequences or it could be structural sequences. Here is the basic idea. In the CNN we use a trick of common parameters for many neurons. Additionally, we also exploited certain structure. Can we do the same two things with recurrent neural networks? We want a neuron's input at any time step to depend on its state s at time t minus 1. Now I must mention that time here is only one possible instance of the sequence. In general, the time t could be replaced, or generally with say index t, and an important example, a running example for the discussion that follows will be that of language models. So let us say you see me writing a sentence here, replay, replac. Could you now predict what the next character should be? Well, the next character was an E, but what are the other possibilities? There aren't too many other possibilities. So let us say E was the most probable one, and now that I have an E here, if I ask you to predict the next character, either you would have a space or you might put a D, and given that I have already predicted replaced, what would be the next character? Generally I would require, so I would have otherwise predicted a W, but when I happen to see M, O, I immediately I am going to change my inference on the following characters. So as you can see, we want a neuron's output at time t to depend on its state s at time t minus 1. We also want it to depend on any inputs that have been seen at the current time step directly. Inputs or signals from the previous time steps or previous position indices will be only indirectly reflected through the state at the previous indices. The other point that we realize in this example is the model that was used to predict an E or a D should not be drastically different from the model that was used to predict an O when you see an M. So the second point here is we would like the same model to recur, the same parameters to be reused. So share parameters across time steps, and that basically means the O that gets predicted after seeing an M is based on the same kind of model, same parameters that predict an E after having seen a C or a D based on the prediction E and after having seen a C, and so on. So that is what we refer to as recurrent. We are performing the same task for every element of the sequence. How would such a model look like? So yes, indeed what we want here is the ability to capture the current input, and this is what the input layer of a traditional neural network will give you. So based on the current input, I am going to make a bunch of predictions through a hidden layer. So I might have a hidden layer here with H1, H2 and so on, and based on the hidden layer of course I can make an output prediction. What is desired here is that the state of the hidden layers after seeing new input is somewhat associated or determined by the state of the hidden layer after having seen the previous input. So let us show the same. So here is my new input, and I am going to connect the same network architecture, the input nodes to the hidden nodes, they will determine the output. Now some points to realize here are that these two are exactly the same network architecture. However, what we want is this new hidden state depends on the previous hidden state. So question is how to encode this dependence. Well, one could do this as follows. One could associate weights for transition from a particular state st minus 1 of a perceptron to another state st of the same perceptron. So again what you see here are the same perceptron, the same network, but at different time steps. Now the weight associated for transition from st minus 1 to st and the weight associated for transition from st to st plus 1 of the same neuron are kind of dependent on the time. Is that really required? Well, what we wanted or we expressed as a desirable property of the recurrent neural network on our previous slide was that these parameters are actually shared, and that is exactly what we depict here on the right hand side. We not only impose a structural requirement, we also talk of shared parameters, which is what makes the network recurrent, performing the same task for every element of sequence while sharing parameters. Is there a way we can reflect this property into the physical neural network? So here is the question we want to address next. Is there a way we can integrate this functional property into the network, the neural network, as a structural property? So, question basically is, how do we translate this functional property into a structural property? So, let us actually see this functionality in action before we translate this functionality into a structural property, and here is our demo. So, you can go to this online demo at cs.toronto.edu, where you are allowed to type in some characters which form the prefix. So, your prefix could be something like the meaning of life is. And you are asking the system to predict a certain number of characters, let us say 20, and let us see what it produces. So, the meaning of life is being based on. Of course, semantically this is not making too much sense, but we do find that there is some structural coherence, there is syntactic coherence. So, syntactically being based on are certainly meaningful, and in fact if you allowed the system to generate more characters, you might find something more interesting coming in. So, let us say I allow it to generate 30 characters. Oh, you do find that the prediction has changed. So, prediction has somewhat changed based on how many characters you want to predict. This can be partly attributed to the number of characters, but also partly to the fact that inference here might involve some sampling. But keeping that aside, we do find that syntactically the output is meaningful. So, the meaning of life is waiting. So, you really have a verb here, and in fact there is a full stop. You could have had a more meaningful verb here instead of waiting, such as the meaning of life is fascinating. Now, how did this neural network really function? What was the structure underlying this functionality? So, let us see the functionality. So, here is the compact representation of the neural network that we have been interested in. On the left hand side, what we have done is encoded this temporal dependence or dependence with respect to the structure as a self loop on the perceptron. So, the self loop says that the state at the next iteration depends on the state at the previous iteration, and the influence is through this weight W. Of course, the state at the next iteration would also depend on the new input. So, this x could have been xt, and it could have been xt plus 1 at time t plus 1. So, the state S at time t plus 1 will basically be a function of the state at time t and the input at time xt plus 1. So if you unroll this network, this is how it would look like. Xt minus 1, xt and xt plus 1 are the inputs at different time instances. The dependence of the states on each other is based on limited memory. So st only depends on st minus 1, st plus 1 only depends on st. St plus 1 does directly depend on the input at time t plus 1, that is xt plus 1. Its dependence on xt is only indirectly through st. So what you see on the right is what we have been talking about as the functional property or the functional characterization, and what helps you achieve this functional characterization is the structural property. Now how does this actually happen for the language model demo that we just showed? Let us start with a simple setting, and let us say we have 3 characters A or B or C. Now the input at any point of time is either an A or a B or a C. A very often used encoding for this vocabulary and the way you let the network know that a particular input was seen is through this so called one hot encoding. So we are going to have 3 bits, a vector with 3 positions, each position is binary, so 0 or 1. The value at position 1, if it turns out to be a 1, it indicates that we have seen an A, and we would therefore require that there are zeros at the other 2 positions. Likewise, position 2 if filled with a 1 and zeros at other places would mean a B, and a position 1 at the 3rd position with zeros in the other 2 is a C. So this is what is referred to as the one hot encoding. Give a unique k to each character in alphanumeric order and encode each character with a vector of vocabulary size with a 1 for the kth element and 0 for all other elements. Now with this kind of language model, how do you predict the next character? Well, what you would like to do is pass on the input to some hidden layer, and this hidden layer of course will in turn affect the output, which could again be one hot encoded. Let us say there are 3 positions here, again we are just trying to predict what are the next characters. So A would typically be followed by a C, and let us say this is what is desirable. How do you make the possible prediction at the current state influence the prediction at the next state? It is through the hidden layer. So hidden layer will have a self loop. This is the structural aspect. Functionally this would mean that I look at its state at the next instance based on its state at the current instance, and kind of repeat this structure or unfold the structure to get the desired functionality. So here is ABC, and we are going to basically connect the input layer, which is going to be an abstraction of ABC to some vector with binary values, vector of size 3. We are going to connect this to hidden layer, which will in turn go to some output layer, but the hidden layer will have this self loop. So let us look at the unfolded network for a slightly more complex setting where you have many more characters, and let us say we are interested in auto completing the prefix MACH. Let us say we believe that this should actually be completed to INE, LEARNING and so on. How does this happen? Well, we look at what character was typed in initially M, and there's some configuration of hidden layer. What we see here is 3 neurons in hidden layer corresponding to 8 input nodes. So this WHX we will assume is a fully connected network, which means there are 8 into 3, which is 24 weights. So what you see here is one instance of time, but the same network was repeated at other instances of time. The output layer for us is again of size 8, and correspondingly there would again be 8 into 3, which is 24 weights. So as far as the initial state of the network is concerned, it does not seem to be doing what is desired. So this first cell, which has 0.3, should have ideally been 1 and the rest 0, but unfortunately what is being predicted at the second position is the character corresponding to this 0.5. We would of course like this to be corrected. Likewise, what is presented in green in these subsequent output nodes is the desired configuration, the one that should actually have been a 1 and the rest 0. Now how do you do this correction? Well, first of all, the WHH is going to connect each hidden node to itself in order to be able to more reliably predict the next character, and these WHHs are going to be trained to be able to get this right prediction. So what is the right prediction? Well, this is what we want. This is a desired state of the network after training, where corresponding to M you see an A, the one here in with value 0.8, corresponding to an A you expect to see a C and an H and an I and so on. So how do you make this happen? So how do you make sure that the configuration of the hidden nodes in that desired state, which leads to the desired output layer, is attained? Well, we have to train the WHX and the WHH. So to better understand this, we write down the RNN equations where the hidden state at time t is a function of the hidden state at time t, ht, is a function of the state at time t minus 1 weighted by WHH plus a weighted linear combination of the inputs from the previous layer plus some bias. The activation function G could be a sigmoid or its extension to multi-class called softmax. So recall that our softmax is nothing but e raised to minus w transpose wk transpose phi x divided by summation over the classes of e raised to minus wc transpose phi x. This is the extension of sigmoid. It will also be tan h, which just turns out to be a scaled and shifted version of the sigmoid function. In fact, a network could also have a combination of different activation functions. Yt is a combination of the HTs. More generally, it could be Yt is summation over I, Wyhi, Hti. I is an index over the nodes in the hidden layer. So the new or the present hidden state depends on the previous hidden states and the present input. The present output depends on the present hidden state and in turn upon previous hidden states. here are our correspondences. Now how do we learn these weights? Well, this can be done through back propagation through time. So of course you will need to do a forward propagation as we have been doing in the past, get your predictions, but to do back propagation we need to realize that the evaluation is actually at the output layer, and we need to reflect the evaluation of the output layer on updates on the intermediate layers, and for us the intermediate layers now also include the transition or the self loops that exist on each of these hidden neurons. So the inference of course proceeds through the hidden layers, the inputs are reflected on subsequent hidden configurations through the current hidden configuration. So at t equals 2 we present x2 as A at input and desire y2 as C as output in one hot encoded form, and this is the form of h2. At t equals 3 we see a C and we desire an h. So putting h1 and h2 in the last equation and then tuning weights through back propagation, you can get the appropriate y3 which correspond to vectors x3, x2 and x1. So this back propagation really requires you to look at what actually came up and based on that re-estimate the weights that would give the desirable hidden states at the previous time steps or the previous indices. So all this is basically to help us tune h1 and then tune y1 so as to get the desired h2, so as to get the desired h3 and so on. The back propagation through time isn't very different from the back propagation we have learned so far for neural networks, just that we will need to account for this very important modification called the self loop, WHH being the weight on this self loop. The rest actually just follows. So as far as parameters are concerned, if you have a sequence length of 4, the parameters for each hidden neuron are just going to increase by 1, this is per neuron. As far as the other parameters are concerned, they are going to pretty much remain the same. So limitation of RNN is that when we train our networks with long term dependencies, the back propagation through time, when we train our networks through long term dependencies, the back propagation through time leads to something called the vanishing gradient. So the idea is that if there are several gradient values v1, v2 and so on, and the absolute values of these v's turn out to be less, the multiplication of v1 with v2 and then v2 with v3 and so on, which happens courtesy the self loop on each perceptron, this leads to the gradients becoming very small and actually tending to 0. The product of these gradients is basically going to lead to no updates for some of these states. One might say that you could use an alternative function that gives value greater than 1 as output, but this will have the other problem, which is your gradients might simply explode. So the idea is to be very selective about which states to use to predict the next state. Do you really need the entire history to matter when it comes to predicting the state based on the current input? So the vanishing gradient problem has been shown here with respect to the unfolded network. So inputs have been shown here on below, there are indices up to 7 and there are hidden layers and outputs which have all been summarized across all the neurons in the hidden layer. The sensitivity of the network with respect to the input, that is the input at t equals 1, varies or decays as you move away from the input, and in fact this decay is exponential, has been pointed out here. So for time 7 steps we find that the first state is extremely sensitive with respect to the input, or rather the configuration at time equals 1 is sensitive to input at time 1, but then the effect of gradient update across these time steps is drastically reducing, exponentially reducing, so much so that any update you do at the 7th state and try to reflect that on the weights that should have been at the hidden layer configuration corresponding to the first time step or the first index is going to be practically 0. So the effect is really vanishing. The solution to this is long short term memory. The idea is we want long term memory but very selectively. So the solution is memory that captures selected history. Selection aspect is what short term is about, and the history component here is what long is about. So procedurally this will mean you learn when to propagate gradients and when not, depending on the sequences. You use the memory cells to store information and reveal it whenever needed. So you are going to basically have something called a memory cell which stores information on when to propagate and when not to propagate. So for example, if you have I live in India, I am certainly interested in the fact that I have seen in India when I try and look at the next possible location. So if I have to predict the location to be a city, I would rather look at cities in India. So you are trying to remember the context India as it is generally related to many other things like language, region, etc. However, once we have mentioned Mumbai, you might want to forget India because you are interested in attributes of Mumbai and not generic attributes of India. More about the long short term memory in the following discussion. Thank you.